Okay, please send through anything you want me to talk about. Again, otherwise this will be the same routine. I'll probably just go through some of the past homework questions or exercises from the text. But if there's a topic you'd like me to talk about, then please send it through on the chat. Okay, so let me put the camera down on my paper. Okay, so let me go through then you can find it okay, 323 part 1. So this was one of those I asked you to do. So prove that if you've got non-zero alpha and beta, then alpha plus beta equals beta if and only if alpha times omega is less than or equal to beta. Here. Okay, so two directions, if and only if, here. So if alpha plus beta is beta, right? That's going to imply that alpha is less than beta. I mean, what we've got is a situation that's like something like here, like 2 plus omega equals omega. And here. Indeed, this would conform to the exercise. 2 times omega is indeed less than or equal to omega. Right? So, in fact, it equals omega, right? So it equals, this inequality is borne out. Right? So what we've got is a smaller thing being added to a bigger thing. And it's so big that it absorbs the smaller thing. Right? I mean, another thing is something like omega plus omega squared. Right? Well, this will turn out to be omega squared. I can think by the laws of distributive law for multiplication here. I've got omega plus omega squared. 1 plus omega is omega. So this then just equals omega squared. So here's another example. Omega plus omega squared is omega squared. And likewise, again, what have we got? We had here alpha is omega, beta is omega squared, and again, so I've got here omega times omega is less than or equal to, or indeed equals omega squared. So we're asked to show this in general, right? So we've got alpha is less than beta here. So what we do is, or one way of doing this, is just to show by induction for every k that alpha times k is less than or equal to beta. Just for finite k's. If I can show that alpha times k is less than or equal to beta, right? So this is just alpha added to itself k times, right, here. So if I know this for all k's less than omega, then, I mean, alpha times omega is by definition the supremum of the alpha times k's for k less than omega here. So this will be then all of these less than or equal to beta, so this is less than or equal to beta, which is what we want. So the tactic then is just to prove this, that alpha times k is less than or equal to beta. So prove this, right, here. So, but if I've got alpha times k here is less than or equal to beta, right? So what would I want to say? Alpha times k plus 1. This is alpha times k plus alpha. Here. Just seeing whether. So if I add beta, then here, this is less than or equal to alpha times k plus alpha plus beta, which is alpha times k plus alpha plus beta. So this is less than or equal to beta. So I've got that this is not quite right. This is then alpha plus beta. This is just beta here. And so not quite there yet. This is just beta plus beta. So I've not quite managed it yet. Alpha times k plus 1. This is alpha times.
Can you just use the inductive hypothesis at the start?
Sorry?
Could you just use the inductive hypothesis at the start? So substitute alpha times k, and then you get alpha times k plus alpha is less than or equal to alpha plus beta.
So alpha times k plus alpha is less than or equal to?
Alpha plus beta, because we have from the inductive hypothesis that alpha times k is less.
So I've got alpha times k is less than or equal to beta. Right. Okay. And the next step would be?
And then alpha plus beta is equal to beta from our assumption at the start.
Oh, right. Yes, I haven't I haven't used this bit. Right. Yes, I haven't used this. So sorry, it's early in the morning. Alpha plus right. Alpha times k. So sorry, I kind of got a blind spot. It should be clear, shouldn't it? Okay, so I'm assuming assuming I know this. This is, and I know this. Right, this is the inductive hypothesis. So now I want to look at alpha times k plus 1. So this is alpha times k plus alpha. So alpha times, so sorry, I'm quite blindsided. What do I say next then?
So then if you use alpha times k is less than or equal to beta from the inductive hypothesis,
Yes.
you can then say, yeah, replace that with beta, and then you can say that whole thing's less than or equal to alpha plus beta.
Well, that's
and then that's equal to beta.
Sorry, alpha times k is less than or equal to beta, right? Okay. So I've got alpha times k plus alpha, right, from here. So this I can say is alpha times k, and alpha is less than beta. Alpha is less than beta, so that's less than this. And alpha times k plus beta, oh, I can then just say this is alpha times k minus 1 plus alpha plus beta here. So then this is just beta. And then I can carry on reducing this all the way down here. Which equals beta. Sorry, I was making a dog's dinner of this. Okay, I don't know whether that, it's not commutative as somebody asked, right? So we can't just in general say for ordinal addition that gamma plus delta equals delta plus gamma, right? Okay, sorry, so let's just go through this once more. I was making heavy weather of this. So we're told alpha plus beta equals beta, right? Alpha is less than beta. We assume as an inductive hypothesis, alpha times gamma is less than or equal to beta. So then alpha times k is less than or equal to beta. So alpha times k plus 1, this is alpha times k plus alpha here. I mean, it might be tempting just to say this is less than or equal to beta plus alpha, but then the non-commutativity kicks in, and I can't just say that's the same as alpha plus beta. Okay, but alpha is less than beta, so this inequality is true here. But I'll take out one of these alphas, so I'll rewrite this as alpha times k minus 1 lots of alpha plus beta. And I know that alpha plus beta is beta. This is our hypothesis. So this just comes down to beta. So I do this k times, right? Just taking out alphas, and I end up with alpha plus beta equals beta here. So now I've got my inequality that I want. And then, as I said, we look at the supremum of the alpha times k's, and that's alpha times omega. And so that means it's less than or equal to beta. I can indeed say for natural number, I mean, for some pairs of ordinals, we do get commutativity. Some pairs of ordinals, gamma and delta, we do have gamma plus delta equals delta plus gamma. I mean, it's rarer, but it happens. So indeed, k plus 1, if k is less than omega, equals 1 plus k. So it does sometimes happen. And indeed, I believe there's an exercise somewhere that says that, but it's not, it's a little tricky to say exactly when that happens. Yeah, actually, if you look at 320, exercise 323 characterizes exactly when we do have commutativity. Okay, so what we've got then is we've done this direction here after all that discussion, right? So let's look at the reverse direction. So what are we doing here? We've got that we're going to assume alpha times omega is less than or equal to beta, right? And we want that alpha plus beta equals beta. Okay, if alpha times omega is less than or equal to beta, so that implies, I mean, alpha is less than beta, because omega lots of alpha is less than or equal to beta. So certainly alpha is less than beta. So now I could just think of how many multiples of alpha plus a remainder I need to get beta. So there exists a chi in a row, which gives us a quotient and a remainder here. So beta is then alpha lots of chi plus rho. So I'm thinking of, here's beta laid out, and perhaps here is alpha. So chi lots of alpha like this will take me up to here, and perhaps the next multiple of alpha would take me too far. So there's just a remainder row here. So that's the picture. Beta is alpha times chi. I mean, it might be exactly alpha times chi, in which case the remainder is 0. Okay, so chi is at least omega, because alpha times omega is less than or equal to beta. By assumption. Okay, we want this. Well, beta's of this form now. So we've got alpha plus beta is alpha times chi plus rho here. By associativity, that is this. And a law of arithmetic, distributive law, that is this. A distributive law. And chi is greater than or equal to omega. So 1 plus chi is chi. Right. And this is just beta, which is what we wanted over here. So stuff coming through on the chat. Okay, let me just, sorry, I'll deal with Josie in a moment. From Jason, don't we need to restrict rho to say omega is less than or equal to chi? No, we're assuming alpha times omega is less than or equal to beta, right? So the quotient, if you like, our omega lots of alpha are less than or equal to beta. I mean, it might be that chi is omega and we've got equality here and rho is 0. That's true if that's what you might be pointing out, right? It could be that chi is omega and rho is 0, all right? But in general, it's going to be some multiple of alpha here, plus a little bit left over. And the only restriction on the bit left over is, of course, that rho is less than another multiple of alpha. Right? So in this quotient remainder thing, it's just like for natural numbers. Beta is chi lots of alpha plus a remainder that's less than alpha. So the restriction on rho is just what comes up of doing this multiplication and finding the remainder here. Is this using corollary 343? Could be. I mean, I'm using the result that I can find beta as this quotient and remainder. Yeah, it's using 343. To express beta in this form here. And someone's got a suggestion which perhaps might make the first part simpler. I'm just looking to see whether Josie's suggestion looks good. Can you see, give us one? And it's alpha times k. This is alpha plus alpha times k. And this is less than or equal to this looks good. So if we go back to the first part again, with alpha plus beta equals beta, and so we have alpha is less than beta, and in fact, as an inductive hypothesis, alpha times k is less than or equal to beta. So Josie's suggestion for a quicker solution is to say, okay, alpha times k plus 1, this looks better. This is the same as alpha times 1 plus k, because this does commute here. So this is alpha times 1 plus alpha times k here. And this is less than or equal to beta. And we're told that this is beta. Good, very good. I was making as I said, a big meal out of nothing, right here. Great, great. Thanks, Josie. Yes. So I hope people see that. That was the trick, was to turn the k plus 1 into a 1 plus k. Yes, thank you, Josie. Again. Okay, shall I do 327? Right, so this is just checking. Sorry, my sheets are a little on the old side. I'm just checking the numberings right. Okay. I've got a power of omega here, some tau, and I got something smaller than this. So it's about thinking about powers of omega here. So then show that there's some delta smaller than tau and a k that's less than omega. And a gamma less than omega times to the power delta. With alpha being omega delta times k plus gamma. So it's asking to express this alpha as, again, a kind of quotient and remainder thing here. So it's going to be some multiples of omega to the power delta plus a remainder, some gamma that's smaller than it. But actually the multiple is only going to be a finite multiple here. And so the chi here is just this k, right? This quotient. Because of the setup, because we've got alpha less than this sigma, which is this power of tau here. Okay, and it depends really whether this is a supremum of smaller powers of omega or not, as to how it works. So case 1, maybe tau is the successor. So this omega tau here, so this form here. So this is omega to the delta times omega by definition of exponentiation here. And again, what is this? By definition of multiplication, this is the supremum of the omega delta times k's here for k less than omega. Okay, so this is looking good. This is looking something like the answer that I might want here. Okay. So alpha is less than this sigma. Right, so this is sigma here. And if I were to draw it out, here now I've got multiples of omega to the delta. Right. And sigma is the supremum of omega of them. And alpha is less than sigma. So alpha falls down here somewhere, right, if this is 0. So alpha is somewhere in here, is the picture. And now we're in the same picture as the quotient remainder business from before here. I know I've got, here's omega delta times 2, omega delta times 3, etc. This is the supremum of the omega deltas times k's. Alpha is somewhere in between. Right? So this means alpha falls in between these blocks here. So for some k less than omega, we have omega to the delta times k. Okay, alpha might be exactly that multiple of it, but it's less than omega times delta for the next block. Right? So in this picture, this is omega delta times k here, and this one is omega times delta, omega to the power delta times k plus 1. So now we use the same corollary then to get a remainder. What was it? 343. We have our remainder gamma. Alpha is omega to the power delta times k plus gamma here. And the gamma is less than the divisor here, omega times delta. So we fulfilled the task here in this case 1, right? We found our k and we found our gamma that's less than delta. Okay, case 2 is when Tor is a limit. Right, so sigma is this omega Tor. So again, sigma is then the supremum, right? Tor is a limit. So this is by definition the supremum of the omega deltas for delta less than Tor here. Definition of exponentiation in this limit case here. So that's all I'm using there. But now alpha is less than this, so alpha is going to have to be less than one of these omega to the power delta guys here. So it's just similar to before. If alpha is less than sigma, then what I've got is omega to the power delta is less than or equal to alpha, but it's less than the next one here. Right, and this delta, these are all less than tau, right, over here. But now I'm in exactly the same situation before. I've got alpha between omega to the power delta and omega to the power delta plus 1. So we're in the same situation. There's a gamma less than omega to the power delta, so that alpha is omega to the power delta. Yeah, I mean, it's exactly the same as before, because here this is omega delta times omega, right? So I've got a K and I've got my
Can you
gamma.
move the page up, please? Thank you.
So it's exactly the same situation. Okay, so you have to show the following. If x and y are countably infinite, then the union is. Okay. So being countably infinite means, again, same definition. Happens to be definition 414 as well. So x is countably infinite. This is defined to mean, x is bijective with omega. So what we've got two sets bijective with omega, and we want their union to be bijective with omega. And you think, okay, this is perhaps fairly obvious, but of course you have to produce the function that does the bijection. That's really the only point here. So suppose I've got some h which bijects x with omega, and I've got a g that bijects y with omega. We want L that bijects the union. Okay. And there's probably many ways of setting this out, and I'm not claiming that this is the only way by any means. So the thing is that we're not told that they're disjoint. How do you? It's just fiddly. How do you find this function L here? I mean, x and y, who knows what kind of overlap there is. I mean, maybe x is a subset of y, proper subset of y, or something like that. We don't know. Okay, so how I set this out is the following. Suppose there's only finitely many things that are in y but not x. So this stuff is finite down here. So let K then be a bijection with this stuff. Here n is less than omega. So it's the finite bit here for some function K here. So I'll define my L. So it'll start out like K. So it's just a question of specifying something. For I less than n. And then what has that done? That's enumerated some stuff in Y here. And then the rest of X union Y is all in X. So we just use H for the rest of it, right? And we've not got any over, we specified here in the range of K, the stuff that's not in X. So here I'll just let this be H of, so what was this? N minus I minus N here. So both parts of this are 1-to-1, L is 1-to-1, and by design it's onto X union Y. So that's case 1. Case 2, otherwise, this is infinite. Sorry, this should say this is finite. Yeah, I mean, in fact, I mean, the exercise is kind of easy. It's just kind of a bit fiddly to write down a specification. So let L on the evens here be HI. So that takes care of X, right? So this puts X into the range of L here. And we now just we do the rest of Y. So Y minus X is infinite. So we just write a specification down. L of, on one of the odds here, I'll just let this be the jth member of Y as enumerated by G here. And well, what is G of J? What is J? So I just pick the least thing that hasn't been mentioned so far. Where J is least, so that G of J, well, it's in Y, and it's not one of the things we've mentioned so far. It's not in X or any of L of 0 up to L of 2I. So we just keep enumerating using the L function things that are in X on the evens, and then on the odds we just pick out a new element of Y that we didn't enumerate already so far. That's the idea, right? So then again, this G should take omega bijectively to X union Y. And we've catered for the case, either of these cases. But this is not the only way of setting this out here. I'm sure you could find other ways of specifying this. But it's asking you to do something like that. So, you know, surprisingly kind of long answer for something that looks kind of like a relatively simple question, right? But it's about constructing a function, right? Likewise, the Cantor-Schroeder-Bernstein theorem, right, which was more sophisticated. We had an X being injective into Y and a Y being injective into X. But then what we had to do was find a bijection. So you had to kind of come up with a function. So this is a simpler situation. But again, we just have to come up with a function that works.